In this section, we will continue with electron configuration. We will look at it in terms of drawing the orbital notation and writing shorthand configuration. Orbital notation is another way of explaining where the electron is located within the atom by showing the grouping and position of the electrons in the atom. We will use arrows to represent the electrons, and we will use a line or a box or sometimes a circle to represent the orbitals of the energy levels of the atom. We've already discussed the off-belt principle. Electrons fill subshells and orbitals so that the total energy of the atom is minimum, meaning that electrons are going to fill the lowest energy level sublevel first and work their way up to the higher energy level sublevels. There are two other rules, however. One is Hund's rule, which is placing electrons in unoccupied orbitals of the same energy level before doubling up. And then, of course, the Pauli exclusion principle, which is two electrons that occupy the same orbital must have different spins. Let me explain Hund's rule. Let's look at the first three energy levels in detail once again. In energy level 1, we know that there is only one s sublevel. And in one s sublevel, there is only one orbital. We're going to draw a single line for that one orbital in orbital notation. In the second energy level, we have S and P sublevels. So once again, the S sublevel can only have one orbital. We're going to draw a single line. But for the P sublevel, there are actually three orbitals. These orbitals are all of equal energy, so when we draw them in orbital notation, we use three lines to represent them. In the third energy level, we have the S, the P, and the D sublevel. Once again, the S sublevel only has one orbital, single line. The P sublevel has three, we'll use three lines. And the D sublevel actually has the 5 different orbitals. Once again, they're all of equal energy, and we must draw all 5 lines to represent them. Hund's rule basically says that when you have orbitals of equal energy, and you need to put in a certain number of electrons, you must put an electron in each orbital first before you go back to make a pair. So let's say we wanted to put 2 electrons in. We would put an arrow in the first and an arrow in the second. What if I wanted to put 3 electrons in? We would put one in the first, one in the second, and one in the third. What if I wanted to put 4 electrons in? I would put one in the first, one in the second, one in the third, and I would go back to put one back in the first orbital to make 4. Lastly, if I wanted to do 5, I would continue 1, 2, 3, 4, and 5, and if I had to completely fill that sublevel orbital, I would go ahead and put my 6th electron down. Which leads us to the last rule, which is the Pauli exclusion principle. And what that says is you cannot have 2 electrons in an orbital of the same spin. They have to be of opposite spin. So when you're putting electrons in an orbital, you must make sure that one arrow goes up and one arrow goes down. So if I was to go back to that situation where I wanted you to put 4 electrons into the 3p orbital, we would do 1, 2, 3, 4. Okay, that would be correct. You could not, however, do this. 1, 2, 3, 4. The fact that both of these arrows are sharing the same space and they're moving in the same direction, that would be breaking the rule of Pauli exclusion principle. By looking at the periodic table, you will see that the electron configuration for nitrogen, which has 7 electrons, is 1s2, 2s2, 2p3. To draw orbital notation for nitrogen, you are simply going to draw your lines to represent the orbitals and fill in the electrons. So we know 1s is going to have one orbital, and there are 2 electrons, so we're going to put one up and one down. We have a 2s. Remember, s sublevels only have one orbital and 2 electrons, one up, one down. The 2p sublevel has 3 orbitals. We'll draw 3 lines. We'll label it, and it has 3 electrons. 1, 2, 3. Remember Hund's rule? We have to put an electron in each orbital first before going back to make a pair. Let's try another example. Write the orbital notation for iron. If we look at the periodic table, we can come up with the electron configuration of iron to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Remember that we can quickly check and make sure that that seems valid if we didn't have a periodic table by looking at the numbers of electrons. If those add up to 26, which they do, that's a good indication that we have a correct electron configuration. It will also identify the element as iron if you went to the periodic table and looked up who number 26 was. As we're doing orbital notation, single line represents the s orbital, 2 electrons for the first one, 2s, we'll have 2 electrons. 2p, remember, has 3 orbitals. All p sublevels have 3p orbitals. They are all of equal energy. There's my 3, 4, 5, 6 electrons that are sitting in them. Third energy level, s sublevel, we have 2 electrons. We'll do the same thing for 3p. Once again, 1 electron in each orbital first before going back to making a pair to complete your 6. We're in the 4th energy level now, s sublevel, only 1 orbital, 2 electrons, and now we get to the d block for the first time. Remember that there are 5 d orbitals, and we are locating 6 electrons. So 1, 2, 3, 4, 5, and we go back to make 6. Just like with electron configuration, there are some types of questions I can ask you. One could be how many valence electrons are in iron, and whether you look at the electron configuration or the orbital notation, the highest energy level is 4, and so we would say that there are 2 valence electrons in iron. I could also ask you about paired and unpaired electrons. If I ask you how many unpaired electrons are in the last sublevel, you would go to the 3D sublevel and realize that there are 4 unpaired electrons. Another way that we can explain where the electrons are within the atom is a simpler method called shorthand notation, or sometimes nicknamed noble gas notation. The noble gas elements are the group 8A elements on the periodic table. They contain helium, neon, krypton, argon, xenon, and radon. All of those elements, with the exception of helium, have 8 electrons in their outer shell. Noble gas notation is used to represent the core inner electrons, which would be the symbol of the element that we'll put in brackets, and only the valence shell electrons will be shown in terms of configuration. If you take a look at the example below, you can see that bromine's complete electron configuration is given to you. Right underneath it, you will see the shorthand notation, or noble gas configuration. The argon is representing all of the elements prior to the valence shell electrons, leaving behind 4s2, 3d10, 4p5. Let's take a look at how to do this on the next slide. When you're writing shorthand configuration, how do you decide which noble gas to choose? It's kind of like the game of Price is Right. How do you win on Price is Right? By getting as close as possible to the value without going over. So what you're going to do is you're going to look at the periodic table, and you're going to choose the noble gas that is closest to the element we are writing the noble gas configuration for without going over. So let's go back and take a look at iron. We know that iron is number 26 on the periodic table. We're going to go back and find the noble gas that comes before iron for shorthand notation or noble gas notation. So remember, your noble gases are in this last column. Since iron is number 26, we're going to go back until we get to argon. And that's where we'll start our configuration. we will put argon in brackets, and then we will move on. So from argon, we would move here to potassium, which is 4, S2. We know that once we get into the D block, it's N minus 1, and this is going to be then 3D, 1, 2, 3, 4, 5, 6. That is the shorthand configuration or noble gas notation for iron. Alright, let's try one more example. We're going to do the noble gas notation or configuration for barium. So the first thing we're going to do is we're going to locate barium on the periodic table. It's number 56. It has 56 electrons. We're going to go back until we get to the noble gas that precedes it. We're going to put that in brackets, which is xenon, and then we start our configuration from there. So of course, as we're going this way to xenon, we're going to go into row 6. This is the S sublevel, and barium is the second element in that sublevel, so xenon 6s2 would be your shorthand notation. Let's do the longhand notation as a quick review, and then we will compare the two real quick. So if we were to start back at the beginning, let me drop my energy level numbers down here to the left. We will start. So we have 1s2. It's going to take me to here. 2s2. 2p6. 3s2. 3p6. 4s2. 3d10. 4p6. 5s2, 4d10, 5p6, 6s2. By looking at the normal electron configuration, you can see that all of these electrons are inner core electrons. The only valence shell electrons would be the ones in energy level 6. So a shorthand notation is a great way of getting important information but not having to write a lot of extraneous information. We are just concerned as we move into the new unit with the valence shell electrons. And so shorthand notation is going to be your best bet. Also remember, as a quick review, that you can go up to the energy, or not the energy level, but the group number of the group A elements, and that will also tell you how many valence electrons you have. Since this is group 2, it has 2 valence electrons.